Hi, I'm Emily, and today I will explain how the Sun and other stars are structured, how solar activity affects Earth, and the hazardous and beneficial effects of solar radiation. The Sun has a three-layered structure: the core, radiative zone, and the convection zone. The core is where nuclear fusion takes place. The temperature of this layer is 15 million degrees Celsius. This core releases electromagnetic energy. The radiative zone is the middle layer. The temperature here is near 8 million degrees. The convection zone is the outermost layer of the Sun and has rising and falling currents of gas. The atmosphere also has three layers. There's the photosphere, the chromosphere, and the corona. The photosphere is the thinnest and the innermost layer. It's several hundred kilometers thick. The chromosphere is thousands of kilometers thick. And the chromosphere is also 20,000 degrees Celsius and produces the most UV rays. The corona is the hottest atmospheric layer and is several million kilometers thick. The density of low gas and emits low electromagnetic radiation. There are four main types of stars. There are main sequence, white dwarf, supergiant, and giant. All stars are made up mostly of helium and hydrogen at some point. Also, all stars are made up of a very hot gas that is constantly exploding. When the stars run out of gas, they burn, they're considered dead. Stars eject much of its material back into space, and this material is recycled and used for new stars. So it's basically a never-ending cycle. Spectroscopy is the science of studying properties of light. This helps answer questions on the matter of energy, time, and space. There are 7 different types of radiation given off by the Sun. Electromagnetic radiation is in electromagnetic waves and are used to transfer energy. This radiation travels at the speed of light. The speed of light is 300,000 km, or 8 times around Earth per second. So it's pretty fast. Radiation is present in 6 different kinds of waves: visible, UV, infrared, X-rays, radar, microwave, and gamma rays. Even though there is radiation in the waves, it is tolerable to the human body as long as you aren't exposed to these things too often or in high matters. The body can fight it off. Humans can only see the visible spectrum. UV radiation comes from the sun, or you probably know it as sunburn. These are also used to sterilize medical equipment and some foods. Infrared radiation is used to determine heat. X-rays are used by doctors to determine the density of the bone or if there are any damage, fractures, or breakages to the bones. Microwave are used in appliances to heat or cook food, and they're also used in communications and radar. Gamma rays aren't that commonly used because they're very dangerous and hard to work with. They are used in cancer radiation treatments. Gamma rays also come from supernova explosions. So although solar radiation helps us every day, it's a double-edged sword because overexposure to the radiation can harm or even kill us. Thanks for watching.
Something surrounds you, bombards you, some of which you can't see, touch, or even feel. Every day, everywhere you go. It is odorless and tasteless, yet you use it and depend on it every hour of every day. Without it, the world you know could not exist. What is it? Electromagnetic radiation. These waves spread across a spectrum from very short gamma rays to X-rays, ultraviolet rays, visible light waves, even longer infrared waves, microwaves, to radio waves which can measure longer than a mountain range. This spectrum is the foundation of the information age and of our modern world. Your radio, remote control, text message, television, microwave oven, even a doctor's X-ray, all depend on waves within the electromagnetic spectrum. Electromagnetic waves, or EM waves, are similar to ocean waves in that both are energy waves. They transmit energy. EM waves are produced by the vibration of charged particles and have electrical and magnetic properties. But unlike ocean waves that require water, EM waves travel through the vacuum of space at the constant speed of light. EM waves have crests and troughs like ocean waves. The distance between crests is the wavelength. While some EM wavelengths are very long and are measured in meters, many are tiny and are measured in billionths of a meter, nanometers. The number of these crests that pass a given point within 1 second is described as the frequency of the wave. One wave, or cycle, per second is called a hertz. Long EM waves, such as radio waves, have the lowest frequency and carry less energy. Adding energy increases the frequency of the wave and makes the wavelength shorter. Gamma rays are the shortest, highest energy waves in the spectrum. So, as you sit watching TV, not only are there visible light waves from the TV striking your eyes, but also radio waves transmitting from a nearby station, and microwaves carrying cell phone calls and text messages, and waves from your neighbor's Wi-Fi, and GPS units in the cars driving by. There is a chaos of waves from all across the spectrum passing through your room right now. With all these waves around you, how can you possibly watch your TV show? Similar to tuning a radio to a specific radio station, our eyes are tuned to a specific region of the EM spectrum and can detect energy with wavelengths from 400 to 700 nanometers, the visible light region of the spectrum. Objects appear to have color because EM waves interact with their molecules. Some wavelengths in the visible spectrum are reflected and other wavelengths are absorbed. This leaf looks green because EM waves interact with the chlorophyll molecules. Waves between 492 and 577 nanometers in length are reflected, and our eye interprets this as the leaf being green. Our eyes see the leaf as green, but cannot tell us anything about how the leaf reflects ultraviolet, microwave, or infrared waves. To learn more about the world around us, scientists and engineers have devised ways to enable us to see beyond that sliver of the EM spectrum called visible light. Data from multiple wavelengths help scientists study all kinds of amazing phenomena on Earth, from seasonal change to specific habitats. Everything around us emits, reflects, and absorbs EM radiation differently based on its composition. A graph showing these interactions across a region of the EM spectrum is called a spectral signature. Characteristic patterns, like fingerprints within the spectra, allow astronomers to identify an object's chemical composition and to determine such physical properties as temperature and density. NASA's Spitzer Space Telescope observed the presence of water and organic molecules in a galaxy 3.2 billion light-years away. Viewing our Sun in multiple wavelengths with the SOHO satellite allows scientists to study and understand sunspots that are associated with solar flares and eruptions harmful to satellites, astronauts, and communications here on Earth. We are constantly learning more about our world and universe by taking advantage of the unique information contained in the different waves across the EM spectrum.